Okay, I think we better get going. Well, welcome to this course on single node optimization for ARCHER2. My name's Mark Bull, and I'm going to be sharing the lecturing and duties with my colleague Adrian Jackson, who will be here this afternoon. So I'm just going to give a quick overview and some administrative details before we get started on the course material. Okay, so the legal stuff. Yeah, my name's Mark Bull. I'm a senior research fellow at EPCC. I'm a lecturer on our master's program, and I'm also our representative on the OpenMP ARB, which is the organization that looks after the OpenMP specification. Okay, won't spend too much time talking about ARCHER2. I'm sure most of you are familiar with it. It's the UK's national supercomputing service, and it's yes, been around for a while now. So just a few numbers about it. So the system has 5,860 nodes with 128 cores per node. And there's each node has 256 gigabytes of memory, except for some large memory nodes, which are double that. It uses the Cray Slingshot, it's actually Slingshot 10 interconnect, and has some large attached file systems. So we'll be looking in more detail about the single nodes in this course, and not really caring too much about the interconnect and the storage. Okay, I will skip over stuff. This is here. These are really here for your reference if required. I'm not going to talk through this. Okay. So at the end of the course, we will ask you to fill in a feedback form. It's always very useful for us to get feedback on these courses and help us continually improve our training service. General inquiries, if you've got specific inquiries about this course, please get in touch with the training account at EPCC. So Claire will answer administrative questions. If you've got technical questions, please feel free to get in touch with me. But if you're having problems with your account, then please get in touch with the help desk. Okay, so you've been invited to apply for project accounts for this training course. So these will be active for a few weeks, for about a month after the course has finished. I just want to remind you that at that point the accounts will be closed and all the files associated with them will disappear, will be deleted. So if there's anything that you do in that account during this course, please remember to copy anything off that you want if you want to keep it. There's a relatively small amount of budget associated with these accounts, so there's plenty for you to do the exercises, but please don't abuse it by running large jobs under these accounts, because it'll disappear quite quickly. Okay, and part of the reason we ask you to do this is that it'll allow you to use a reservation to access some dedicated nodes and get quick turnaround on jobs for the practical sessions. And I'll come to some more details about how that works later on. But it's absolutely fine if you already have another ARCHER2 account. If you want to use that, that's fine. You won't have access to the reservation. If you submit jobs to the short queue, then most likely you will get reasonably quick turnaround on them anyway, because they're all nothing requires more than a single node. Okay, so all the course materials are available on the ARCHER2 website. So if you navigate via the training tab to the page for this course, there's a link to a GitHub repo with all the materials. Just a reminder: if you clone that repo, make sure that you change to the branch for this course. Okay, so there's the repo contains branches for previous runs of the course. So if you to get access to the right set of materials, you need to swap to the current branch. Those materials will be archived on the training page. It will move into the past course materials page, but they will be kept semi-indefinitely. So you'll always be able to come back and have access to the course materials. Okay, expect everybody to abide by our code of conduct. So basically that means just be nice to everybody, and not just that doesn't mean just me, it means all the other attendees on the course. Okay, some more information about funding calls. Again, that's really for reference. So just a quick overview of the timetable we're going to do. So this morning, after this introduction, I'm going to be talking mostly about hardware. So giving a background on some modern processors and memory, and describing the single node architecture that we have on ARCHER2, and then start with a practical session on memory performance. We'll have a break at 11 o'clock, and then after that I'll be talking about profiling, and there's a practical session with associated with profiling. Then we'll break for lunch, and this afternoon Adrian will be talking about how to use the compiler to improve the performance of the code, and then there'll be practical sessions after that. And then tomorrow morning I'll be talking mostly about shared memory, OpenMP optimization issues, and again there's a practical session associated with that. And then in the afternoon it'll be Adrian again talking about vectorization and optimizing for the memory hierarchy. Okay, yeah, so there's the link, the direct link for the direct URL for the course notes. I shall paste that into the chat window as well in a moment. So the practical exercises, so the source code is in the repo, but it's also available directly as just for you to copy on ARCHER2. So you can just copy it directly from this shared directory. It's a tar file, so then you just have to unpack it. But make sure if you're not familiar with ARCHER2, when you log on, you automatically get into your home directory, but you need to change to your work directory in order to be able to submit any batch jobs. So I recommend that you just do everything from your work directory. Okay. So I mentioned the reservations. So these are the reservation IDs. So again, I will paste those into the chat window for you to copy as well. So basically, when you submit a batch job, you use the sbatch command, and then -- reservation equals whichever number it is for today. Let me get a pointer up. Okay, so instead of this res ID here, you substitute for today this number, or for tomorrow that number. Okay, and then the name of the script that you want to submit. And inside the script, you may need to edit it so that it changes the QoS value to reservation. and that should then run on the reserved nodes, and you should get a quick turnaround on your batch jobs. Okay, hope you enjoy the course. Please do ask questions. The easiest way to do that is probably via the chat window. So I'll keep an eye on that as we go along, and also stop at various points to invite questions. So you know, please use that, and I'll try and respond as quickly as I can to questions posted in the chat. Okay, so let me just post those useful bits of information into the chat window. Okay, so Max asked, that's a very good question. What's your work directory? Okay, when you log on, your working directory will be /home/ta213/ta213/ your user ID. So you want to change to a directory which has just replace home with work in that path. So it is explained in the practical session notes. So if you are in, so you want to, your home directory will be something like this. And then you want to change to that directory. Okay, and that's the reservation ID for today's sessions. But we can sort it, if you have any problems, then we can sort it out at the start of the first practical session. So don't worry too much just now. Okay, does anyone have any questions before we begin? Okay, good. So this first session is really intended to give us a reasonable appreciation of the hardware features. So it's useful for us as programmers if we want to do code optimization, to at least have, we don't need a full, very detailed understanding of how all the hardware works. I mean, I certainly don't, so right down to the low-level electronics details. That's not something that I know about, but it's useful to have at least a reasonable mental model of how the hardware operates, so that you understand when you're modifying code what it is that you're trying to achieve, and what might be what are likely to be the bottlenecks for performance, and how you might improve your code. It's useful to have an understanding of the hardware. So that's what I'm going to try and give you in this first session. Okay, so if we think about the fundamental pieces of hardware that are put together to make an HPC system, there's really four principal technologies here. There's processors to do the calculation. There's the memory to store the working data for the code. There's the interconnect, which enables the processors to talk to each other and also to the outside world and to the storage system. And then there's the storage system itself. Okay, so it's the disks for storing your input and output data. And in other systems, you might have, for example, tape storage for long-term archiving. But we're going to focus for this course. We're going to focus on the first two of these. We're going to be focusing on processors and the memory. Okay, so the processors, so very simply, their basic functionality is to execute instructions to perform arithmetic operations. So that could be either integer or floating point. They are able to load data from memory and store data back from memory again, and then make the decision about which instructions to execute next. So follow the control flow through the code. In modern processors, all the arithmetic is performed on values in registers. So the registers are the local storage inside the processor. So inside every core, there is a small amount of storage. And moving data between memory and registers has to be done explicitly by load and store instructions from the processor. So there will typically be separate register files for integer values and floating point values. May also be separate one for storing addresses as well. The typical size is fairly small, so 64, 128 values would be fairly normal. So there's a relatively small amount of storage, which the arithmetic units can use as their inputs and outputs. Okay, and so some of the basic metrics for processors are the clock speed. So that's essentially the rate at which instructions can be issued. And also for HPC simulations, we're possibly interested in the peak floating point capability, which is just some multiple of the clock speed. It's just the clock speed multiplied by the number of floating point operations that can be delivered in the same clock cycle. So the clock speed just determines the rate at which instructions are executed. So modern processors are around a sort of 2 to 3 gigahertz range. That's been true for quite a long time now. We are seeing some indications of that creeping up a little bit in newer processors, but not very much. So that's kind of where we're stuck with clock rates. So integer and floating point calculations can be done in parallel. You can also have multiple issue. So it's possible to do, for example, in some systems it's possible to do an add and a multiply at the same time. Yeah, so the peak flop rate is basically just the clock rate times multiplied by the number of floating point operations we can do in every clock cycle. And to support all this and make it all as efficient as possible, there's a whole series of hardware innovations. So there's, which we'll talk about a little bit in more detail, there's pipelining, out-of-order execution, speculative computation, vectorization, vector units, which I'm going to cover in a little bit more detail. Okay, so you've probably all heard about Moore's law. So, roughly speaking, it says that CPU power doubles every 18 months or so. Well, strictly speaking, that applies to transistor density, but that sort of translates into, in some sense, into how much computation you can do. It's been true for, well, more than 40 years, probably 50 plus now. Has it ended? Not completely. So that rate has probably slowed down a bit. So it's probably more like 2 or 2.5 years now rather than 18 months. But as I said, the clock rates have reached a plateau for quite a long time now. So in the past, a lot of the increased compute power was gained by steadily increasing clock rates, but those have pretty much completely plateaued. And further increases in compute power are really due to increases in parallelism rather than increases in the clock rate. And that consists of parallelism at various different levels. There's some very fine-grained parallelism, which is pipelining. So that's basically within instructions. There is some medium-grained parallelism, which we'll talk about a bit more, superscalar issue, SIMD or vectorization, and hardware multi-threading. And then there's coarse-grained parallelism. So this is basically having multiple processors, multiple cores on a chip. And in terms of hardware design, the first two of those, the fine grain and the medium grain, seem to be pretty much exhausted in the sense that don't seem to be any further realistic gains to be had from those technology innovations. And almost everything now is almost all the power, the compute power gains. And what do you do if you have more transistors on your chip because you shrink the process? What do you do with them? The only really gain that's being played now is just to add more cores. And so we've gone from a handful of cores to the chips in ARCHER2 are quite old now, but they have 64 cores. We're now seeing, so if you look at the very latest generation of AMD chips, we're getting like 144 or 196 cores on a chip. So that is the only that's the only meaningful way that we're getting more performance out of conventional CPU processors in the current era. It's just to get more cores. Okay, so let's have a quick tour of what's inside a CPU core. So functional units are the basic building blocks, and how many and what type they are do vary with the different designs. But in any processor, we'll find at least the following ones. So first of all is the instruction unit. So that's responsible for fetching, decoding, and dispatching of instructions to other units. So it gets the instruction from the instruction cache, it decodes it, and then sends because it's stored in a compressed form, and it then sends the instruction to the appropriate unit. It may also have some responsibility for scheduling instructions, and we'll come back to talk a bit about that later. We'll also have integer units. So these handle the integer arithmetic. So addition, multiplication, division, and also logical operations. So like bitwise and, or, bit shifts, and so on. It's also referred to as arithmetic and logic unit. So ALU is the terminology used for that. We have the floating point units and handle floating point arithmetic. So typically addition, multiplication, division, sometimes square root as well in hardware. And that's obviously usually the critical resource for most HPC codes. So there's all machines are sold, advertised, and marketed by their peak flop rates. What other things we have? A control unit. So that's responsible for executing the branches and jumps. So if the instruction stream wants to change from just executing the next instruction in sequence, wants to go somewhere else in the code, the control unit is responsible for that. Then we have a load store unit. So that's what's responsible for loading data from memory and storing it back again. And then, as we already talked about, there's the register file. So this is the local storage in the CPU. And when it says accessed by name and not address, it means that the register file is not part of the memory system. Okay, in some sense, it's the top level of storage, but once things get into registers, then we lose the information about what memory address they came from. And then typically modern processors have also all other bits and pieces as well there. So memory management hardware, the cache controller, bus interfaces, potentially graphics and multimedia capabilities and all sorts of other stuff. Okay, so let's start looking at some of the hardware features which are designed to maximize performance. So pipelining is the sort of lowest level of parallelism in the CPU. And so the way this works is that the execution of each instruction is broken down into stages, where each stage can be executed on one CPU clock cycle. So all the parts of the CPU operate at the same fixed frequency. So once a stage has been completed for one instruction, the idea is that it can be executed for the next instruction on the subsequent clock cycle. So this mechanism allows one instruction to be completed per clock cycle, even though the instruction itself may take many cycles to complete, because it consists of lots of different stages. Okay. So the chips in, for example, the chips in ARCHER2, the AMD ROMs, they have a 19-stage pipeline. Okay, so that's actually the maximum length for any instruction. Not all instructions will take 19 cycles to complete. However, most of pipelining mostly just happens, and there's not very, it's a low-level hardware feature. There's not very much we can do to influence it as a programmer. One of the important things to note is that not all instructions are pipelined, and in particular, floating point divides and floating point square roots are typically not pipelined. So that means that if your code contains lots of divides and square roots, they are expensive operations. That's because they take lots of clock cycles to execute. So typically something like 20 or 30 clock cycles to do a divide or a square root, but only one of those instructions can be happening at a time. So you don't get this effect where you can deliver one result per clock cycle for instructions like this. So that's just useful thing to know, is that that floating point divides and square roots are expensive, and we should try to avoid them as much as possible. Okay, so when everything's working fine, pipelines are great, but things can happen that prevent pipelining, or means that the pipeline has to stop and restart, and cycles get wasted as a result. So, for example, if two instructions both require the same hardware resource, the same functional unit at the same time, then they have to take turns. Okay, so that's not too bad, but worse is when what happens if one instruction depends on the result of another instruction further down the pipeline. So if we do a multiplication and then do a test on that multiplication to decide what to do next, then the test instruction can't immediately execute. After the next instruction, or the next multiply instruction, would have to wait for that test to happen first. And also, so the results can change the control flow. Okay, so various hardware tricks that are tried to avoid this happening. One of these is out of order execution. So I don't know if you've ever done this, but you might have looked at the assembly code that the compiler produces. So when you look at the assembly code that is in the executable, what that specifies is a sequential order of instructions. But in fact, what that order doesn't, the instructions don't actually have to be executed in that order. And the hardware can actually choose to reorder them in order to try and minimize pipeline stalls and use the pipelines as effectively as possible. And it requires some quite complicated bookkeeping to ensure correctness, right? So to ensure that any reordering doesn't affect the result of the program. But that is all going on underneath, which is something which might not necessarily realize, is that, the order of instructions in the assembly code is not necessarily the order in which the instructions actually get executed in the hardware. The other thing hardware tries to do is branch prediction. So whenever there's a branch in the code, the hardware tries to guess which way the next branch is going to go. So it basically uses a hardware table that tracks the outcomes of recent branches in the code. And that what it does, it'll guess, and it will keep the pipeline going, and will only stall if it got the prediction wrong. So it will do partial execution of instructions kind of in a speculative manner, and it'll only squash those instructions if the branch prediction turns out to be wrong. Okay, so pipelining is the very lowest level of parallelism in the processor. So let's move up a level now and look at instruction level parallelism. So you can think of pipelining is a low-level form of instruction level parallelism, in the sense that multiple instructions are in flight at the same time, but the maximum you get from pipelining is one instruction per cycle. It's also possible to have instruction level parallelism at a higher level, and so it's possible to identify instructions that can be executed independently. So, for example, those that use different functional units. So, for example, you can have a load instruction and a floating point instruction can be issued on the same clock cycle. So there's two main approaches, both of which are important. Processors are superscalar, So what does that mean? It means that the parallel instructions are identified at runtime in the hardware. So this can be combined with the out of order execution. So what the processor is really doing is it'll actually, instead of loading one instruction at a time, it'll load a batch of instructions and then decide what the right order is for them, and also which ones can be issued on the same clock cycle. So there's, the processor does quite a lot to reorder and exploit parallelism at the instruction level when it's loading the instructions. The other approach, so both of these are important. The other one is SIMD, so single instruction, multiple data, or vector instructions. So these are instructions where operations on multiple data items are encoded in a single instruction. Yeah. So for superscalar processors, yeah. So this is the basic idea is just to divide instructions up into classes which use different resources. So yeah, maybe integer and floating point would be the most obvious one. And then if two or more instructions are in different classes, they can be issued on the same clock cycle and proceed in parallel. Yeah. So for example, an integer add and a floating point multiply could be issued on the same cycle. And as I said, this process can be combined with out of order execution to do the full parallel and out of order instruction scheduling. So this is done in hardware, yeah, and it's although the scheduling can be helped a bit by compilers, but this is mostly a hardware feature. Okay, so the compiler can help a bit by trying to order the assembly code in a way which favors multiple issue, but most of this is done on the fly at runtime in the hardware. So SIMD instructions, these are instructions, yeah, which encode operations on multiple data items. So for example, if you can imagine a simple floating point instruction might encode for C equals A plus B, but an SIMD instruction could encode for both C equals A plus B and F equals D plus E in a single instruction. So and it could be more than two, so it could be depending on the hardware and also depending on the size of the operands, whether they're 32-bit or 64-bit. So you might get a single instruction might encode, say, for 4, 8, 16 floating point operations. So most modern processors have support for these. So it requires a substantial extension to the instruction set. So you have to have basically SIMD versions of all your normal instructions. And it requires, and obviously for this to make sense, you have to have multiple arithmetic units and usually some additional registers to take advantage of them. And a bit of terminology here is the SIMD width is the number of operations encoded in a SIMD instruction. So yeah, so typically 2, 4, 8, maybe 16 for small words. So that sounds great, but in practice there are some restrictions on what SIMD memory operations can do. So imagine what is a SIMD memory operation going to do? It's going to load multiple data items instead of in one instruction instead of a single data item, a single word of memory. So for example, there may be some restrictions there. If a 2-word SIMD load of double precision values may only work if the values are actually consecutive in memory, so they actually belong in neighboring addresses, and are also aligned on a 16-byte boundary. So there can be restrictions like that that mean that you can only use these SIMD operations in certain circumstances. And this is a job for the compiler. Okay, so when the compiler compiles your source code, it's responsible for identifying operations which can be combined and encoded into these SIMD instructions. And in practice, this is a tough job for the compiler. Okay? And this is because things like the alignment of data is often not determinable at compile time. So, you know, does this array element lie on a 32-byte boundary? Well, the compiler can't always tell. So to get around that, to some extent, the compiler is able to generate multiple versions of code in the assembly code, and then pick the right one depending on how the alignment that happened at runtime. So there are some ways around that, but you know, to fully exploit it may require using hints or potentially even, you know, in the extreme hand-coded assembly. And Adrian, tomorrow afternoon, Adrian will talk about, there'll be a session about vectorization and how to help the compiler, how you can rewrite code, give the compiler hints to help it in its job of generating SIMD instructions. Okay. So obviously it's now completely commonplace to have lots of cores on a chip. So typically each core will have its own level 1 and level 2 caches. The level 3 cache is shared between some set of cores. It's also been possible in the past, and I don't see this too much as either, to have cores sharing functional units. So thankfully we've kind of got away from that now. There have been some past designs that were like that, which were rather painful to use, but thankfully that's not really a problem these days. So the kind of typical design is, okay, my diagram's gone horribly wrong here. Okay, so ignore this box that says chip, please. Okay, that should encompass all the CPU's level 1, level 2, and level 3 caches. So typical to have, you know, cores. Each core has its own level 1 and level 2 cache, and then some set of cores shares a level 3 cache, and then the main memory is external to the chip. So this means that multiple cores on the same chip can communicate with with low latency and high bandwidth. So because the reads and writes which are cached in the shared cache, but cores can contend for space in the shared cache. Yeah. So this is kind of a little bit more detailed, and we'll come back to this, talk about this more in. We're talking about optimizing for the memory system. Most importantly, cores share off-chip bandwidth. Okay, so for access to main memory, and this is a serious problem in modern processors, as we'll talk about in more detail. Is that the memory bandwidth is often the constraining factor in the performance of a lot of HPC application codes. So it's really not the floating point performance that's the critical resource. The floating point units are not the critical resource for many applications. It's actually memory bandwidth. Okay, so that got a bit. Got a little bit out of order there somewhere. Okay, empty. Yeah. Okay. Most modern processors are superscalar, okay, so they can issue several instructions in every clock cycle. So typically this is, you get 4 or 5 instructions per clock going to different functional units. But the problem is that most typical applications don't have that much instruction level parallelism. Okay? So if you look at the assembly code and you work out where are the dependencies between the instructions and say on average how many instructions could be executed at the same time, then the answer is maybe about, for typical applications, it's around 1.5 or 2 on average. Okay. So what that means is that, although the processor is capable of issuing maybe, 4, 5, 6 instructions per clock cycle, in practice, a single application can't use them all because there are too many dependencies between the instructions. There's too many ordering constraints. So one feature that is used to try and fix this is simultaneous multi-threading. Okay? So unfortunately, this is a feature which goes by a lot of different names. Okay, you might have heard of hyperthreading. So that's the same thing. That's just Intel's terminology for it. Virtual cores is also the same thing. Hardware threads, also the same thing. So unfortunately, there's lots of different terms which are used to refer to the same hardware feature. Okay. So what that does is the way that this tries to work is to try and fill those spare instruction slots by mixing instructions from more than one thread in the same clock cycle. Okay. So you have two or more completely separate instruction streams active in the hardware at the same time, and on any given clock cycle there can be instructions coming from more than one instruction stream. So this requires some replication of hardware. Okay, some additional silicon has to be devoted to supporting this. So you need some extra stuff, but it's only kind of the order of like 5%. So for example, Intel Xeon designs, it turns out about 5% of the chip area is used to support this feature. But everything else is shared between the threads. So functional units, register file, memory system, etc. But again, this is how much can you do this? So typically, for most architectures, 2 or 4 hardware threads is simultaneous hardware threads is all that makes sense. So most x86 designs, so including the AMD ones, it's just 2. So here's kind of an illustration of how this is kind of intended to work. So you can imagine that. So suppose that I've got a chip with 5 instruction slots. Okay, so across here is supposed to represent the 5 different instruction slots. So it could be basically this one might be load store. These 2 might be integer ones, and these 2 might be floating point ones, for example, something like that. So you can imagine that if I ran a particular sequence of instructions from 2 different threads on 2 different cores, they might occupy instruction slots like this. So in this one, this is the red thread. So where the box is red, that means that there's an instruction was actually issued. Okay? And it can't use all the instruction slots because there are some dependencies between the instructions. Okay, so it might be that, so for example, this instruction here can't execute until the previous one has until this one is completed, or there will be dependencies between the instructions. Okay. But a different thread running on a different core might have a different pattern of usage of the instruction slots. So that means that if we could, if you imagine, instead of running those on two different cores, if we combine those two threads and run them on the same core and allowed the instructions from the blue and the red thread to be mixed, so then we could get through those sequence instructions. You're going to fill more of the instruction slots, and the processor will be more efficient. Okay, so you might not exactly be able to get full parallelism. Okay, so in this example, you actually need, because of the dependencies, there's a clash somewhere where both threads need the same unit. So it's so in this case it took 6 clock cycles to get through these sets of instructions, but by combining them, we can get through them in say 7. Okay, so that's the basic idea of SMT, is to be able to mix instructions from more than one thread of execution and utilize the processor more efficiently, because by definition, if the instructions are coming from different threads, there can't be any dependencies between them. Okay, so does it actually work? Well, it also obviously depends on the application, depends on how the threads contend for shared resources. So if for example, so you can imagine if both those threads were doing dense matrix multiplication, then probably every single clock cycle, all the floating point instructions are filled up. So that's not going to help. But more generally, you might get some benefit. But in practice, if you have 2 hardware threads, you're never going to, you very rarely see 2 times speed up. You can very occasionally, but in practice, it's you get like 1.2, 1.3 times speed up. As I say, yeah, if they're if both threads are using the same functional unit, so the floating point units intensively, then you won't see the benefit. And in practice, it can actually slow things down. You get increased contention for memory bandwidth and cache space, but most importantly, in sort of HPC context, the real problem is that in order to exploit this kind of parallelism, that has to be explicit in the code, so that these execution threads would either be, for example, OpenMP threads or MPI processors. So in order to exploit 2 hardware threads, you would need to either double the number of MPI processors for your application, or equivalently double the number of OpenMP threads. And if you do that, what tends to happen is that the overheads associated with parallelism, with that additional parallelism, such as additional communication or additional load imbalance, actually outweigh any benefits that you get. So for that reason, we typically don't use it by default. So on ARCHER2 and on most other HPC systems, the batch system, so Slurm, is set up in such a way that applications by default don't use this feature. So you only get 1 MPI process or 1 OpenMP thread per physical core. You can tell Slurm that that's not what you want, and you want it really to use this feature. But that's that's not the default case, and that's the reason why it's done like that, is that for most applications it actually makes things worse. Okay. I'm not going to say too much about accelerators, and so because we don't have any, well, we only have a very small number of GPUs as a test system in ARCHER2, so I'm not going to talk very much about that. We do have a complete course on GPU programming now as part of our training schedule. So if you're interested in that, then please keep an eye out for the next run of that course. But so very briefly, current popular trend for HPC systems is to have additional special purpose processors alongside the main CPU. So these typically have large numbers of relatively simple cores. They have high memory bandwidth and a separate memory system from the CPU. And so mostly these are GPU systems these days. So they're relatively low cost because they're essentially a small variant on a mass market product for graphics cards. They are harder to program, and for some applications, the cost of moving data to and from GPU memory is actually the critical bottleneck, and that's quite difficult to optimize. But there's been, so that's probably what we're going to end up with in the future. So I think it's highly likely that the system that replaces ARCHER2 in a year, 18 months or so will probably be a GPU-based system. Okay, does anybody have any questions at this point? Okay, good. So let's move on a little bit and talk about memory. So in reality, so the memory performance is actually really the limiting factor for a lot of HPC applications. It's not the floating point units. So keeping the CPU fed with data is actually the key to performance. And memory is a substantial contributor to the cost of systems. So our typical HPC systems only have a few gigabytes of memory per core, and the reason for that is it's not a technological limit. It's technically possible to have a lot more than that. You can easily there's no problem if you wanted to. You can easily put multiple terabytes of memory in a node, but it's very expensive and consumes a lot of power. So the choice of the amount of memory is kind of a trade-off between what applications need and what's affordable. So key metrics we might care about are latency. So when the processor requests a data item, how long does it have to wait to get it back? Bandwidth, what's the sustained rate that you can feed data from memory to the processor? Okay. And ballpark figures, well, it's sort of 100 nanoseconds more for latency as an order of magnitude. It's quite big, and per core, it's a few gigabytes per second. Yep. So memory latencies are long, so it's order of 100 processor cycles. So this is. So, effectively, fetching of data from main memory is 2 orders of magnitude slower than doing the actual arithmetic. So if all we had was the CPU cores and main memory, then we would, then the memory accesses would be completely dominate the performance. So the solution, or at least partial solution to this problem, is to introduce cache memory. So this is a small amount of memory placed between the CPU core and main memory. It's much faster than main memory, but in order to achieve that, it's also very much smaller than main memory. And what it does is it keeps copies of recently used data, so that if a data item is accessed more than once, then only the first access hopefully takes the cost of the load from main memory, and subsequent reaccesses are much faster. And modern systems use a hierarchy where it's typically three levels everywhere now, and it's and they're all on the chip. So typical modern systems have a memory hierarchy that looks something like this. Okay, so we've got the CPU core at the top with its registers. So this side is the speed. Okay, so how long does it take to get data, and on the right hand side is how much is stored there, the capacity. And so as we go down the hierarchy, the cost increases, but the capacity also increases. So typically we have the CPU registers, which are accessible in a single clock cycle, but there's order of a kilobyte of storage in there. And I have a level 1 cache, so it's maybe 2 or 3 cycles to access that. So order of 100 kilobytes of storage in there. A level 2 cache, which is maybe 20 cycles, something like that, order of a few megabytes. Level 3 cache, say this is typically shared between groups of cores on most systems, but maybe having something like a 50 cycle latency and tens of megabyte capacity. And then you have main memory, which is gigabytes of capacity, and might take something of the order of 100 or 200 clock cycles to access. Okay, so this memory hierarchy is very complicated in the hardware, so it needs a lot of sophisticated bookkeeping. So it has to keep track of where the most up-to-date copy of data is. It has to flush old, not recently used data downwards to make space for new data that's been recently accessed. But this is all done automatically. It's completely transparent to the CPU. All the CPU is doing is issuing load and store instructions. And how the data moves through the caches in the memory system is essentially entirely transparent to the CPU. So that means that the programs still see the simple register memory model. All you see in programs is load and store instructions. And so it just thinks memory is this external thing and doesn't know anything about the complications of its implementation. But kind of true but obvious statement is that caches are good, but they only help performance if the application actually does reuse recently accessed data. And it's mostly the programmer's responsibility to do that, to ensure that, to order our computations so as to maximize the reuse. So the caches do what they do, but it's in order to exploit what they do, then we have to order our computations in such a way that data gets reused as much as possible. Modern systems also do prefetching. They make, relatively simple guesses as to what data is going to be used next, and try to load this data into caches before the processor requests it. So this is particularly if you're making, if the processor is making linear accesses through an address stream. So consecutive accesses in memory to array elements would be an obvious example. Then the hardware can recognize that pattern and try to load the data before it's actually asked for by the processor. Okay. So this means that we're relying on what's called principle of locality. So thankfully, almost every program does exhibit some degree of locality. So a tendency to reuse recently accessed data. And we can think of this as two types of data locality. There's temporal locality, so locality in time, which says that a recently accessed item is likely to be reused again in the near future. So if a variable X is read now, it's likely to be read again or maybe written soon. And the second type of locality is spatial locality, in that items with nearby addresses tend to be accessed close together in time. So, for example, if the ith element of an array is read now, it's quite likely that the i+1th element is going to be read soon. And caches actually exploit both these types of locality. Yeah, so caches hold copies from data from main memory locations. They can hold recently accessed data items for fast reaccess, and it's much quicker than, for level 1 cache, it's much quicker than accessing main memory. So it's 1 nanosecond, order of a nanosecond instead of order of 100 nanoseconds. So a bit of terminology. So a cache block is the unit of data which will be transferred from main memory into the cache. And this is normally a few words long. So it's typically 32, 64, 128 bytes are typical sizes. Again, there's terminological duplication here. The term cached line is also used. So, but they mean exactly the same thing. A cache block and a cached line are just different terms for the same thing. So these are the units of data in which are moved between memory and cache. So when does data get cached? Well, essentially, what we'll do is always cache when data is read. Except in some special circumstances, which I won't go into. If a memory location is read and there isn't currently a copy in the cache, okay, so that would be termed a read miss, okay, because it's a read action and it's a miss because it wasn't currently in the cache. Then that data will be fetched from main memory and a copy will be stored in the cache. What happens on write's a bit more complicated. I'll come back to that. Okay. So where does the data go? Okay, well, the cache is divided into sets, where a set is a small group of blocks. So typically 4, 8, or 16 blocks. And the terminology you'll see here is that if there are 8 blocks in a set, then it's called an 8-way set associative cache. So what happens is if we want to cache the contents of an address, what happens is in the hardware is that essentially we ignore the last, we look at the address and we ignore the last n bits where 2 to the n is the size of the block, okay, in bytes, and then just compute the set index as the remaining bits modulo the number of sets in the cache. So that's just extracting the next m bits out of the address, where 2 to the m is the number of sets. And then the data can go to any block in the set. Okay. So for example, so here's an example. So I've got a cache with a capacity of 32 kilobytes. the block size is 32 bytes, and there are 2 blocks per set. So it's a two-way set associative cache. So each block is one of these. Can contain 32 bytes of data. So for this cache, there will be 1,024 of these blocks to make up the 32 kilobytes of storage. There's 2 blocks in every set, so there are 512 sets in the block. So if the CPU loads data stored at this address, then what will happen is that when that's fetched from memory, it will basically look at strip off the, so this is most significant to least significant bit on the right. So strip off, because the block size is 32, so that's 2 to the 5. So we basically ignore the last 5 bits in the address, because that basically just tells us which word in the block is being accessed. And then the next, so 512 is 2 to the 9. So to get the set index, we look at the next 9 bits in the address. Okay, so in this case, that binary number translates to 412 in base 10. So that will go into the 400. So this data will be stored can be stored in either of the 2 blocks in set number 412. So we've got a choice. So the set in which the data goes is completely determined by the address, but which block in the set is going to be used is a choice. So then what happens is there's probably already some data in that block, so that'll get overwritten. And the normal policy used is the least recently used. So the cache will keep track of for every set of which block has been unused by the CPU for the longest time. Okay, so this is basically just exploiting temporal locality. Okay, the least recently used block is probably the less likely one to be used again soon, but not necessarily. Okay, it's a simple algorithm, but it's not necessarily perfect. There are actually some variants on this. There's a bit more sophistication possible, though in practice it's quite hard to know what caches are really doing, because the details of these policies are commercially confidential, and they're not. There's no documentation that tells you what the processor is actually doing. Okay. So what happens is when so if the data is in the cache, how does it get found? So whenever a CPU loads an address, the cache has to check whether it has the data or whether it needs to pass the request on to main memory. So for a given address, it has to find the set where it might be cached. So to do that, basically what happens is that along with the data, what's called the address tag is for every block is stored. So this is basically just the high-end bits, okay, from the address. So we've got the block offset at this end, we've got the set index, and then the rest of the bits in the address form the tag, and that's what gets stored in the cache along with the data. So basically what happens is that if the CPU loads this address, it knows automatically just by looking at these bits which set it might be in, and then it has to go and check all the blocks in that set to see if there's a match for the the address tag. But that's this is designed so that it's very, very efficient. Finding the set index is just a direct lookup of some bits in the address, and then there's a relatively small search to do, because the number of blocks in a set is typically quite small. So there might be 4 or 8 matches to make to try and detect whether the tag is to detect whether this address matches any of the blocks currently in the cache. So it's often easy to think of, well, the way caches work is highly simplistic. Wouldn't it be possible to do something a bit more sophisticated? And the answer is, well, unfortunately, the algorithms that are used for in the hardware have to be very simple in order to be efficiently implemented, so that they don't take up too much silicon, and so that they don't take too long to actually execute. Okay, so next up is what happens on a write. Okay, so writes are in real programs, writes are less common than reads. But there's 2 different ways that caches can operate. The first one is called write through. So in this case, what happens when a write happens, then the new data will be stored in the cache block, and it'll also propagate the new value into main memory as well. And for this strategy, you normally wouldn't cache on a miss. Okay, so if the data is not currently in the cache, you don't fetch it from main memory first and then modify it. You basically just bypass the cache and just make the modification to the copy in main memory directly. The other possibility is write back. Okay, so in this case, the new values are only written to the cache block, and then the copy of that updated value back to main memory only happens when that block gets replaced by some new data. And you also use an extra bit to indicate when that's necessary. Okay, so when a block's replaced, if it hasn't been modified, then there's no need to copy the values back to main memory because they haven't been changed. If they have been modified, then the new values have to go back to main memory. Okay, and again, remember that all this has been done at the level of entire blocks. So even if a write has only modified one word in a block, then when it's replaced, the entire block gets copied back into memory. And in this case, you would normally cache on a miss. Okay, so if you write a piece of data, if it's not currently in the cache, it'll get fetched from main memory first, and then the cached copy will be the one that's modified now, and main memory will only be updated later when the block is replaced. Okay. So there are advantages and disadvantages to both these strategies. So with write back, not all the writes have to go through main memory, so that reduces some memory bandwidth requirements, but it's a bit harder to implement than write through. Because with write through, main memory always has a valid copy, so that's useful for some purposes. Okay. So what does the processor see? Well, so again, to emphasize that all this machinery is essentially invisible to the processor. The assembly code is scheduled assuming the data is in the level 1 cache. If it isn't, then the processor has to wait until the data is found and loaded. So the processor can continue executing instructions, but there's a limit on the number of outstanding memory references that can be present in the CPU at any one time. So there's a limit as to how many unresolved memory references, how many uncompleted loads there can be at any one time. And once that limit gets exceeded, then the processor will just stop. Okay, it just ceases executing instructions and waits for data to come back from memory. Okay, I think I'm going to skip over virtual memory because it's really not important for modern supercomputers. Okay, ARCHER2 is typical. It only uses physical memory. Okay, so there's no way, once you run out of physical memory, it doesn't spill out to disk. Okay, your application, once you're out of memory, your application just dies. Okay, so I will, in the interest of saving some time, I will skip over the virtual memory stuff. Okay, we talked a little bit about this before. So prefetching. So yeah, one way to reduce the cache miss rate is to try and load data into the cache before the load is issued. So the processor has to be able to support multiple outstanding cache misses, as kind of already just talked about, and additional hardware is also required to keep track of the outstanding prefetches. But the number of outstanding misses is limited because it costs hardware and there's diminishing returns. So hardware prefetching is actually pretty simple. Okay, so basically, whenever a cache block is loaded, then fetch the consecutive block in memory. Okay, so this works really well if your application is accessing memory in sequential order, because that pattern is recognized. So typically, what happens is that if you access two consecutive blocks in memory in order, then it'll start prefetching the third block and the fourth block and the fifth block and so on. And it's possible to have multiple streams. So what that means is there can be prefetching streams coming in starting from different addresses. But again, there's a limit to those, to the number of consecutive prefetch streams that can happen. It's also possible that the compiler can do something here, but it doesn't really work very well. Okay, so most the processor has the capability of issuing an instruction that says, please prefetch this data from memory into the cache. But this is the compiler generated prefetching is largely ineffective. And the reason for that is that the compiler doesn't have enough information about the memory access patterns typically, or it doesn't have enough information about sizes of things, like it doesn't know how big arrays are, it doesn't know how long your loops are in many cases. So it's a very difficult job for the compiler to do this effectively. So mostly we tend to rely on the hardware prefetching mechanism. Typically, we have multiple levels of cache. Okay, so as we've indicated, they increase in size. So otherwise, there's no point. Okay, if the second level cache isn't significantly bigger than the level 1 cache, then all you've done is basically stored the same data twice. So that doesn't help. Because typically to make the bookkeeping tractable, everything that's for example, all the data that's stored in level 1 must also have a copy in level 2 as well. Okay, so that's a requirement to make keeping track of where everything is easier. So that brings us on to cache coherency. And this is kind of, main difficulty, or one of the main difficulties in building multi-core systems is cache coherency problem. Okay, because the hardware is trying to present us as a programmer with the illusion that there is just this simple processor plus memory model. Okay, and it's tried to present us with a programming model that is, there's a shared variable that has a unique value, that the program variables have a unique value at any given time, even though they might be accessed by multiple cores. But where we have multiple cores and every core has its own caches, that means that if multiple cores are accessing the same memory location, there could be lots of different copies of the same memory location in the hardware at any given time. But the hardware has to avoid the two processors caching different values of the same memory location. Okay, so the terminology used here is the caches must be kept coherent. So this is complicated, but the one-line summary is, in order to achieve this, every time a write is made to a memory location, all the other copies of that memory location has to be removed from the caches that they're in. Okay, so whenever a memory location is updated, then all the other copies have to get trashed. Okay. Again, I think in the interest of time, I'm going to skip over some of this. Okay, but the important consequences of this is that is something called false sharing. Okay? Because this operation of trashing out-of-date copies happens to entire cache blocks. Okay, so even though a write might only modify one word in the cache block, then all the other cache blocks containing that address have to get trashed. So this gives a problem. So what happens if, say, two processors, okay, so two different cores, happen to be writing to different words that lie on the same cache line? So this is a problem that can arise in multi-threaded programs. So there's no actual data values being shared by the processors. They might be writing to, say, different elements of an array that happen to be close together in memory, or different elements of a data structure that happen to be close together in memory, and hence stored on in the same cache line or cache block. Okay. So what's going to happen is, in that case, is that each write will invalidate the copy in the other processor's cache. Okay. So that causes a lot of memory traffic, so every time that happens, when a data item has been trashed, then it has to go and retrieve the up-to-date copy from wherever it is in the memory system. So that's something to be aware of, and it's something we'll talk about again tomorrow. Okay. And lastly, about memory, we talk about distributed shared memory. Okay. So again, so the mental model you might have is that the main memory is a single monolithic block of memory, but in fact it's not physically organized like that, because if you eventually the access to that single block of memory, so if you've got so a system like ARCHER2, you've got 128 cores. if they were all trying to access the same block of memory, that would become a bottleneck. So what's actually done instead is that main memory is split up into different pieces. Okay, and these are connected together, but still to give the illusion of a single address space. Okay, so it supports a single address space. So it looks like shared memory, even though the memory is actually physically split up into blocks. Okay. And again, so what happens is that every memory address will be allocated into a fixed location. Okay, so in these multiple memory blocks, when the first time a piece of data is accessed, then it gets allocated into one of these blocks of memory. Okay, so these are called so terminology here is NUMA, non-uniform memory access. So these blocks are usually referred to as NUMA regions. And there's potentially a problem here because every NUMA region of memory is associated with some subset of cores, and accesses from those cores to other NUMA regions in memory do take a bit longer. Okay, there's an additional latency cost, and there's also a problem that if all your the main problem is that if all your, again, we'll talk more about this tomorrow, if all the data ends up on the same, if all your program data ends up in the same NUMA region, then again you have this problem that the access to that becomes a bottleneck. So I will return to this in the context of OpenMP optimization tomorrow, because that's where this has the biggest impact. Okay, so let's just finish off by taking a look at the ARCHER2 node architecture itself. So using all the ideas that we've covered so far. So an ARCHER2 node has two AMD Rome 7742 processors in it. So each of those has contains 64 cores, and each of those has sets of, basically each of those has two lots of 64 gig of memory. So, but okay, I'll talk about the NUMA region architecture a bit more in a minute. Okay, and then these two processors are connected together with an internal network fabric. And then each of the processors has its own connection out into the Slingshot network. Yeah, so each processor has, so we've got two processors in a node, each of which has 64 cores. The clock rate is nominally 2.25 gigahertz. So that's actually the base clock rate. The processor supports turbo boosting. Okay, so if the power consumption isn't for a particular core is not too much, then that can be increased up to just over 3 gigahertz. But actually what we do is on the system is capped to 2 gigahertz by default, because what we found is that for most applications, say again, because it's memory that's the bottleneck, not the flop rate, then reducing the CPU clock rate actually saves power. And for most applications, it doesn't impact the performance. But you can request if you want to run at the full clock rate, then you can. But by default, it's reduced down to 2 gigahertz. So each core has two floating point vector units which execute fused multiply add instructions. So you can do, so this is basically an add and a multiply encoded in a single instruction. It has 256-bit wide AVX vector instructions. So for double precision, that's each of those is 4 floating point operations in a vector instruction, and you've got 2 units. Okay. So if you add that up, so the multiply add counts as 2. You've got 2 units. You've got 4 wide vectors, so that gives you a peak of 16 flops per clock. Okay, so multiply by the clock rate, 36 gigaflops per second per core, and then multiply up again by number of cores and the number of chips in the socket. Then so it gives you about 4,608 gigaflops per second per node. And in terms of SMT, yes, it does support 2 hardware threads per core, but the scheduler does not use these by default. In terms of the memory hierarchy, every core has 32 kilobytes of level 1 cache. It's 8-way set associative, and the line size or block size is 64 bytes. Level 2 is 512 kilobytes. Okay, same set associativity and line size. Each set of 4 cores, which what AMD call a CCX, a core complex, share one level 3 cache. So that the level 3 cache, so these are 16 megabytes shared between the 4 cores. It's 16-way set associative and also has 64-byte lines. So effectively, that's although if you're using all 4 cores, which is what most applications do, then effectively you've got 4 megabytes of L3 cache per core. There's 256 gigabytes of main memory, except for the high memory nodes, and that's split into 8 NUMA regions. So each socket has 4 NUMA regions. So every set of 16 cores effectively is attached to its own block of main memory. But every core is able to access all the 256 gigabytes in the node. So it appears as a single shared memory, even though it's actually physically split up like this. The memory bandwidth, if all the cores are being used, then the peak memory bandwidth is around 3 gigabytes per second per core. And the memory latencies are something like 4 to 8 cycles to level 1 cache, 12 to level 2, 39 to level 3, and 270 to main memory. So those are kind of not exact figures, but they give you some idea of the size of the memory latencies. Okay. Yeah, so we have 4 of these NUMA regions per processor. The memory bandwidth is basically proportional to the memory regions. So we have 16 cores per memory region. So scattering across processors, if you're underpopulating, okay, so if you're running fewer MPI processors and you have cores, then spreading them across the different NUMA regions will improve the memory bandwidth. So again, that's how Slurm is configured by default to do that. Okay. So again, we'll mostly for pure MPI programs, this doesn't really matter too much. You don't really care about it. But when we come to looking at hybrid MPI plus OpenMP or pure OpenMP codes, then we need to think more carefully about this, and we'll discuss that tomorrow. Okay, so I apologize. I've run quite a I've run on quite a lot longer than was timetabled. But does anybody have any questions? Okay, so what I suggest we do is actually make a start on the practical session, but well, yeah, I'll stay online for the next 10 minutes or so. If anyone has any problems connecting to ARCHER2, then just give me a shout, and then we'll take a full break at 11:30. Okay, welcome back, everybody. So in this session, I'm going to talk a little bit about profiling and give a bit of an introduction to the CRAPAT profiling tool. So what is profiling? So it's a process of analyzing your code to find out the proportion of execution time spent in different routines. And so it's really absolutely essential to know this if we're going to target optimization activities effectively. Okay? So this is, it's kind of obvious, but there's really no point optimizing routines that don't significantly contribute to the overall execution time, because all that's likely to do is make your code less readable and maintainable. So we always tend to find that there's a tension here between optimizing code tends to make code less readable and less maintainable. So we always have to strike a balance here, and that's not necessarily a very easy judgment call to make. It depends very much on the usage of the code. It depends whether how machine specific the optimization might be. If you're optimizing for a particular hardware platform, then it's possible that that may even damage performance on other hardware. So it's a tricky call. I say it depends very much on the usage of your application code, who else is using it, what you expect its lifetime to be. Are you intending to, do you think somebody in the future is going to need to, somebody other than you is going to need to maintain and or extend the code, and what you are doing to it. So it's always a balance, and try to, when we're trying to do optimization, then it's always worth considering that, can we do it in such a way that doesn't affect the readability of the code too badly. So code profiling is really the first step for anyone if we're interested in performance optimization. It's always kind of the first thing you want to do. And so it works by essentially instrumenting the code. Well, usually at compile time. Doesn't have to be. Some tools are capable of instrumenting binaries. So this depends a little bit on which tool you're using and what you're doing. Conventional old-fashioned profiling was basically controlled by compiler flags. These days it tends to be done by other mechanisms, by external tools. So standard profiles tend to return data. The simplest information you get is the number of calls to every function and the amount of time spent in sections of code. So that's typically at the function call level, but it may also go down to code blocks or even you go to source code lines and potentially down to individual assembly instructions. Though as you go down that hierarchy, the attribution of time tends to get less reliable. So even though you can in principle ask a tool to attribute code to individual assembly instructions, exactly how reliable that is somewhat gets somewhat questionable. So you have to start taking that information with a little bit of skepticism. So as well as execution time, can also return some hardware specific data. So tools can interface with hardware counters in the chips and get information that includes things like cache misses, TLB misses, cache reuse information. Okay, so how many, what the ratio of hits to misses was, flop rates, utilization of vector instructions, all that kind of thing. That can be very useful when you're looking at in-depth performance optimization, though I have to say it is quite difficult to do. And part of the reason for that is that it's very dependent on what hardware counters are actually supported by the chip that you're working on. And especially for ARCHER2, unfortunately, the AMD Rome chips are not particularly well provisioned with relevant hardware counters for performance optimization, which is a bit of a shame. So specifically for ARCHER2, the amount of information that you can get from the hardware counters is it's not nothing, but it's somewhat limited in its usefulness, I would say. So profiling tools use two different mechanisms for analyzing code. So first one, the basic one is called sampling. The basic operation, the way profilers work, is that they sample the program counter at regular intervals, and it's normally the interval is normally the same as the OS interrupt frequency. So it's normally about it's usually 100 times per second. Which is, if you think about the clock rate, which is, gigahertz, this is it's a relatively coarse sampling. The advantage of this method is that it's very low overhead, so it has very little impact on the execution time. And if you run for long enough, then you basically build up a statistical picture of which routines the code is spending time in. Okay, so basically so basically every 100 times a second, basically say which is the current instruction being executed, and then attribute that to a particular function. So one thing to beware of with sampling is that if the runtime is too small, so I would say anything less than about 10 seconds, then there aren't enough samples for good statistics. So even at 10 seconds, you're only taking, that's only 1,000 samples. So you think if you just do this sort of simple standard error calculations, then at 1,000 samples, your results are only accurate to about plus or minus 3%, which may be good enough. Okay, but any less than that, you can get skewed samples because you don't have enough data. The other mechanism that profiling tools use is called tracing, and you can get some more detailed information by essentially recording some data. So, for example, at least a timestamp at the entry and exit to every function. So that has higher overhead. So it can have larger effects on runtime. So you have to be a little bit more cautious when using it. So if you do this for, if you have functions that take very short execution times, then the additional overhead of doing this tracing can be quite substantial. Some tools do make some effort to try and subtract out their own overheads, but that's not always 100% reliable by any means. And again, this can also result in, if you're not careful how you do this, then you can end up with gigantic output files, which then become extremely difficult to analyze. As whatever you do, whatever the post-processing or moving around files of this kind of stuff, you can get, you can easily get, multiple tens or even hundreds of gigabytes worth of data if you're unlucky. And so just trying to feed that into the post-processing and into tools, or moving those files around, can get very unwieldy and impractical. Okay, I'm not going to spend much time talking about standard Unix profilers. They do exist, but they are typically controlled by compiler flags, but nobody much uses these anymore. So I'm going to kind of skip over that. Just to say that, but the sort of information that you get out though is fairly typical of a lot of profiling tools. So it'll tell you. So for example, for your code, it'll tell you something about different functions in the code down the side here. It'll give you the percentage of the execution time. Okay, it might give you an absolute value of execution time. It'll also, these are ordered by, in this case, these are ordered by execution time. So it'll give you a cumulative time. So this is the partial sum of this function plus everything above it in the list. It'll tell you how many calls were made to that function, and then also tells you what the cost was in milliseconds per call. So this is the typical kind of basic information that you can get out of profiling tools. Okay, so I shall skip over that. Okay, so golden rules. Okay, so this is a bit of preaching. Okay, profile your. You definitely need to profile your code. Okay, if you're at all interested in the performance, then it's absolutely essential that you get some information about where it's spending its time. Okay, I say this is maybe a bit strong, but it's always worth profiling the code yourself. I think large applications, mythology builds up about them as to where the expensive parts are, and that can be misleading. Okay, even if you speak to code developers and ask them, okay, which are the most expensive functions in the code, they may not be able to tell you, or they will give you an opinion which is incorrect for a particular input data, for the particular input data sets and the particular hardware and configuration and program configuration that you're interested in. Okay. So now, again, it's important to profile on the hardware that you're interested in running on, and also to try and use a full-sized problem to run the profile on a problem that's at least representative of the sort of production usage that you're expecting of the code. Okay. And again, that's very application dependent. There are some applications which will pretty much give the same profile no matter what the input data is. There are other applications where, depending on the input data, they may execute very different code paths. So there are some applications which have lots of options, which will trigger completely different execution paths. So it's really important to try and use a representative data set and a representative problem size. So designing a good test case for profiling can be quite difficult, because obviously you don't really want to be using long production runs. You don't want to be running 48-hour jobs just to do profiling. So in many cases, it's reasonable to most application codes repeat the same calculation over and over again. It's either iteration, it's either time, physical time steps, iterations of a solver, that kind of thing. So most applications do typically repeat the same pattern of calculation over and over again. So it can be reasonable to restrict your profiling runs to cases with small numbers of time steps. But then you also have to say, okay, if I cut the number of time steps down too far, then am I really just is my profile being skewed by initialization or finalization phases that I don't really care about in the production case? So you might be concerned about that. Also, you might find that for some applications, the first n time steps are not representative. So maybe the load balancing doesn't settle down very well for the first few time steps, or maybe the load balancing is always really good for the first few time steps, and that's not representative of the whole run. So you might end up, say, rather than starting from the start of a simulation, it might make sense to do your profiling from a checkpoint to restart the simulation from a checkpoint that's somewhere in the middle of your simulation run, and so that you're getting something that's representative of the performance of what you expect from long running application production runs. Another important thing is that don't just do it once. If as we go through the optimization process, it's always important to keep reprofiling and see what's changed. Okay, so that you will, if you've done a really great job, then you might say, well, actually, this routine that I've been working on is no longer really the main computational bottleneck, so it's not worth expending more effort on that, and you need to go and focus on something else in the code. So it's important to keep to generate good test cases for profiling, and then also to keep rerunning them as you change the code to see what's changed. So talk a little bit in specifics about the CRAPAT tool, which is it's the standard tool which is supplied by HPE on ARCHER2 for profiling. So CRAPAT is capable of both doing statistical sampling and function or loop level tracing. So the usual recommended usage pattern is to build and instrument your code, and then run the code and get a statistical profile. And then, depending on whether that gives you enough information or not, you might then want to re-instrument the code using that profile to select certain parts of the code or certain functions, or exclude certain functions for tracing, and then rerun again with the more detailed tracing instrumentation. So CRAPAT has two modes of executions it has a sort of a quick and easy version, and then a slightly more complicated and more detailed version. So the quick and easy version is enabled by loading this PerfTools Lite module, and then rebuilding your application. And then you don't have to do anything. Just the act of loading this having this module loaded and doing the rebuild will do the instrumentation automatically. And then when you run the application, you'll get performance profiling output in your Slurm output file, and you will also get another file generated, which encodes the execution name and then some random number afterwards. One thing to watch out with CRAPAT is that it requires you to keep the .o files around. So just watch out for build processes that either that automatically clean up .o files, or ones. Another common one is a common problem is build processes that move .o files or rename directories, rename the directories containing .o files. So that confuses CRAPAT, because it needs to go and look basically when it's running. It needs to have access to the .o files. So in order to get all the data that it needs. So yeah, make sure that you don't delete your build process doesn't delete or move the .o files. So that can be a bit of a nuisance. Okay, I don't think this is good. This may show up very clearly on your screens, so my apologies for that. So please go and if you might need to go and look at the original PDF files for this, and if this doesn't show up very nicely. Okay, so but I can zoom in a bit. There we go. Okay. Hope that helps. Okay. So this is the typical basic information that you will get from a Perf Tools Lite instrumented CRAPAT run. So what it does is it gives you a total. Okay, so let's say for the whole code it constitutes 100%. Okay, no surprise. It doesn't actually give you time here. What it does is it counts the number of samples. So you can kind of roughly convert that into time, but it doesn't do that automatically for you. And then it breaks down, by default, it breaks down the execution time into 3 classes. So the first one that you see here is MPI. So this is time spent in the MPI library. And then the second class is user. So this is basically user code. Okay, so this is your application code. And then the third one is etc. So that's usually system library code. So things like IO routines or system calls will show up in etc. And then within each of these classes, you then get a breakdown by function. Okay, so it'll break down the total MPI time. So in this application, it spent out of the 100% of execution time, 54.4% was spent doing MPI, and of that, 51.6% was in MPI all-to-all and 1.4% in MPI all-reduce. Okay. So that's already giving you a pretty good indication that it's this application is the performance is really being dominated by MPI all-to-all communications. And then also it tells you that okay, so 41.7% was spent in actual application code. And then there's a breakdown by the different functions here. It tells you also something about imbalance, okay? Because by default we're thinking about multi-processed MPI code here. So it's basically trying to tell you something about these percentages are averaged across all the MPI ranks. So what the imbalance is trying to tell you is basically how much of that varies across the ranks. So basically, it's I think it's is it max? I'm not sure, I can't remember whether this is maximum minus minimum or maximum minus average percent. So that's the kind of basic profile information that you get out of a simple instrumented run. It'll also give you a slightly more detailed breakdown. So it'll actually this is all in text output. So this comes further down the text file that comes out. So you can it also gives you the same information, but also breaks it down into. It also helpfully gives you the location of the source files for your functions, and also will break stuff there. Give you some information about line numbers. Okay. So I think by default, CRAPAT truncates everything that takes less than 1% of the execution time. So by default, it doesn't show you any function. It basically, there are probably more functions in the code here, but it truncates this list when it gets down to 1% of the execution time. You can change that. Okay, you can turn that threshold off completely, so it shows you everything, or you can reduce it or increase it. So you can, so it defaults to 1%, but there's you can change what it does. So again, so what this is doing here is giving you breakdown. So for these functions, these more expensive functions, so this rebound function, which took 10.5% of the execution time, it identifies code at line 77 and line 78, taking each of those takes 3 and a bit % of the execution time. So it gives you a bit more of a clue as to exactly where the time is being spent. As kind of indicated before, you need to take these line numbers with a slight amount of skepticism, okay? Because what's really being inserted here is assembly code. And the tool is trying to map assembly instructions back to the source code line that generates them. But because of all the optimization and reordering and everything that the compiler does, that's not an exact process. So you should look at these with a little bit of skepticism. It probably gets the basic block of code correct. So it probably gets the right, it'll be the right loop probably, okay, or the right loop nest, but the precise line number may not be actually correct. So do beware of that somewhat, okay. So it's still helpful because it'll probably help you identify the expensive loops. But you shouldn't treat the precise line numbers as being 100% reliable. Okay, so that's the sort of the quick and easy version. To get more detailed information and have more control, then instead of loading PerfTools Lite, we do load PerfTools without the -lite on the end. And again, we need to rebuild the application, but then you also need an additional step here. You need to take your executable, so I've just assumed it's called a.out here, but whatever your executable is called, and then run pat build, okay, with this option here, with this -o APA option on it, and that gives you a instrumented application. So what it does, and this again is slightly annoying, is that this gives you an instrumented executable, and it has the +pat extension on the end. So it gives you a new executable with a different name, which is slightly annoying, because then you need to reflect that in your when you run it. Okay, so that may not be, depending, if you've got some complicated scripting going on that's used when you run your code, then changing the name of the executable may not be completely trivial. And it's very easy to forget about that. So then again, if you run the instrumented application, so that's the executable with the +pat extension, again, that gives you you will get you'll either get a single file or multiple files in a new directory created for you. So then to get the text output and also this additional instrumentation file, you then run pat report either on that output file, the .xf output file, or the directory, depending on which it produced. Okay. And then the APA file gives you also will tell you things about, okay, it'll give you some hints about where to put what to do with the additional instrumentation. So you can then run pat build again and pass it this .apa file, and potentially you can pass some other options here as well to control what it does. So this will then give you yet another new binary with a +APA extension, and then you can run that and get your text report, and also potentially also a visualization file over it. So the workflow here is a little bit messy and complicated. Okay, so if we're interested in looking at single core performance rather than MPI performance, so we need to pay attention to the user routines that are consuming the most amount of time, and possibly looking at some of the key hardware counters. So the ones that are, as I say, the AMD ROMs are somewhat limited in what you can get, but useful things you can look at are sort of level 1 and level 2 cache metrics, and also how well it's using vector instructions. So CRAPAT does have mechanisms for finding the hotspot in a routine. Okay, so for example, if you have routines which contain a lot of code, long loops, or lots and lots of loops, so you can do that. There are ways of doing that. You can actually put function calls from the CRAPAT library into your application to label specific regions. So you can do this. You can also use another possible thing you can do for the API is with the CRAPAT API is to turn profiling on and off during the run. So that's useful if you want to, say, exclude an initialization phase from your profile. So you can add function calls in the CRAPAT API to turn the profiling on and off at certain points in the code. So you can, and you can also set an environment variable to determine whether it's on or off when the code starts executing. So that can be a useful way if you have, if you want to try and make the runtime shorter, but you want to exclude initialization or finalization phases from your profile, is to add these function calls that turn the profiling on or off. Okay. You can also do some. This only works with Cray compiler, so I should say that CRAPAT does work with both Cray and GNU compilers, but there are some features which are only work with Cray. So you can use this extra flag hprofile generate, and then you get these additional loop level statistics. So the sort of information you can get with hardware counters. Again, let me make that a little bit bigger. Okay. So for a given function, okay, so this tells you this is in the user class, and for this particular function called remap. So for example, you can get some information. So this is just repeating the information from the flat profile. So the percentage of time, and this is where it actually converts it to real time rather than just numbers of samples, which is maybe more useful. And then you get all these raw hardware counter values, which are by and large incomprehensible and not much use. Okay, so not quite. So you can, some of the things you can see here are the types of floating point operations. So you can see essentially that these are, you can tell whether these are SIMD operations or scalar operations. So again, it's more complicated than what you'd like, but you can use some of this information to get some indication of how well your code has been vectorized. And Adrian will talk a little bit more about this, about vectorization and how to use these kind of statistics tomorrow. So you can also, but it also gives you some derived metrics here, which are possibly a bit more useful. Okay. So it's basically aggregating. It says, this line here tells you this is the total number of floating point operations executed in the hardware divided by the user time. Okay, so that basically gives you a measure of the floating point performance here. Okay, so that's 2.5 million floating point operations per second. So 2.5 gigaflops, I guess. And that tells you, and it says, okay, that tells you that's about 12% of the peak double precision performance that you could possibly get. And well, is that good? Well, yeah, that's quite good. Okay, so for it depends a bit on the type of application, but for most applications, that's which are sort of dominated by memory bandwidth anyway. 12% of peak is quite respectable. Yeah, and then so it also gives you some information about cache accesses. So it says, in the level, so D2 is the level 2 data cache. So that's basically level 2 cache. It says that 94% of the accesses to that were hits and 5.6% were misses. And then you can also see that the tool is trying to estimate how much overhead it introduced. So it thinks it caused a 11% overhead just from the instrumentation. So that can also give you that's a little bit on the high side. That's a little bit more than you'd really like. Okay. But at least it gives you some some quantitative measure of how much the execution time has been skewed by the actual act of doing the profiling. Okay, yeah, so you can see that you can get this hardware performance information. Say it's available on both on a per program. You can get statistics for the whole program, and also, as we've just seen, on a per function basis. Though the per function information is only available once you do the tracing run rather than the sampling run. And the number of simultaneous counters you can get is limited by the hardware. So you can't access all the hardware counters on a given run. So if you need more than that, you'll have to run multiple times. So the way you can control this is by so one way to control this is by setting an environment variable at runtime. So in your job script, then you are you are asking for, you can ask for a particular set of performance counters. And so there are actually 8 different sets that you can choose from, and if you do, you can use the pat help command, and if you go down the command tree, so if you do pat help, then counters, then roam, then groups, it'll tell you. And you can also do man. There's also a man page on hardware performance counters. Okay. So there are some predefined ones. These are the predefined ones here. So these include basically different subsets of performance counters to try and look at different features of performance. So here's an example one. So this is the so-called memory bandwidth one. So it collects a particular set of performance counters, and then tries to give you some statistics. So although it's called memory bandwidth, unfortunately, what it doesn't do is actually give you a memory bandwidth figure. Okay, but it does give you something like it does give you an L3 last level 3 cache hit and miss ratio. So you can give some indication of how much of your data is coming from the level 3 cache and how much is coming from main memory. Okay, so in this case, it's 14.3% of your memory accesses are coming from main memory, and that's higher than you'd like. Okay, it may not sound very much, but because main memory accesses are so expensive, this means that there is some potential here for improving the runtime. So again, these are somewhat limited usage because this is counting misses. It doesn't really tell you how, what you really like to know is what fraction of the runtime can I attribute to the fact that I'm getting these L3 cache misses. And that's what these performance counters don't tell you. Okay? Is they give you counts of things and percentages of things, but they don't really they're not really able to translate that back into a fraction of execution time attributed to certain hardware events. So that's somewhat unfortunate. Okay, so to remember that by default, the performance numbers you're seeing are an average across all the MPI ranks. So which explains why there's some, why some things which you think should be integers are actually not. Okay, and that for many applications that's fine. If all your MPI ranks are doing the same thing, but that's not always true. So, for example, you can have, applications where, MPI rank 0 is special and is doing something very different, or you can have runs where you're doing basically you're running multiple executables. You're running an MPI program that consists of, where different ranks are actually running different executables. So it's possible to filter as part of the report command. It's possible to do some filtering. Okay, so you can use PEs. So this is Cray terminology for processing elements. Okay, so that means either. So that typically makes, for MPI programs, a processing element is an MPI rank. They choose not to use MPI rank here because it works for other programming APIs like Shemem and so on, or Coarray Fortran or stuff like that. So they use an abstract name for of PE, which stands for processing element. but effectively for MPI programs, PEs are MPI ranks. So you can say, okay, you can specify some condition to filter on. Okay. So you can look at individual ranks or average over subsets of ranks if you need to. Okay. If your program uses OpenMP, okay, so either on its own or in conjunction with MPI, then you can also get some OpenMP information out of CRAPAT. So it will give you some, it'll tell you some measurements of overhead incurred when, for example, entering and leaving parallel regions or work sharing constructs within parallel regions. And then also so timing, some other data are shown per thread rather than per rank. Again, this can be somewhat confusing as to when you're looking through the output. You know, what's being averaged across? Okay, are you averaging across threads in a rank? Are you across ranks averaging for the same thread number across all the ranks? So it can get a bit confusing as to what you're actually looking at in the profile. Okay, so again, this is one of these features that only really works usefully with the Cray compiler. You can add this -GOMP option to pat build, which basically adds tracing points, adds these automatic tracing points around parallel regions. So you can also get, you can look at load imbalance across threads as well as across ranks. And as I say, exactly controlling and looking at interpreting what you're looking at can be quite complicated. Okay. Another thing that CRAPAT's useful for is monitoring memory usage. So, you know, you've got limited, in some sense, limited memory, and you know, because systems like ARCHER2 don't support virtual memory, if you run out of memory, your application dies. So it can be useful to know how much memory your application is using. And so you can ask questions like, you know, what's the minimum number of cores you're going to be able to run this problem on? You know, is the memory usage scaling well, or you know, is it balanced across the ranks in your application, or even is my application? You can also say, look at, you know, is my application spending time doing allocates and frees? So in particular, so one of the tables in the CRAPAT output is the heap stats. So this is so basically it tells you so for each, it tells you what the maximum memory usage was for your program, and it tells you how many, the numbers of allocations and frees that happened, and also basically also tells you what was not freed. Okay, so you can look for, gives you some this is, you know, it's not as good as, you know, full memory analysis tools like Valgrind or something like that, but it gives you some indication as to whether memory is not, whether you're getting memory leaks. Okay, and so it also gives you, so what these additional lines here are also doing is it shows you, again, this is something that the CRAPAT output does in other cases as well, where it says MMM here, these are minimum, median, and max across the ranks. Okay, so it tells you, so in this case there wasn't very much difference. Okay, so this is it tells you that. Oh, so which were, maybe I haven't got the order correct there. I think, okay, I think it's mean, or that's the largest value. So that must be the maximum, followed by the mean, followed by the minimum. So it gives you the rank number. So it says the most memory was used by P0 and the least memory by P43. Okay. What I've shown you so far is all the text output. There is a GUI for looking at for examining some of this output. You can say, again, normally running, as with most things, running GUI, if you actually run the GUI on ARCHER2 and export your display back, the performance across the network tends to be terrible. You can install desktop versions of this on your own system. It's okay. I wouldn't say it's particularly, as profiling GUIs go, it's a bit clunky. It doesn't show you a great deal that you can't get out of the text files. But if you like such things, that's cool. Okay. But I'm not going to go into detail about how to use it. Okay. So yeah, just to sum up then, profiling is essential to identify performance bottlenecks. So CRAPAT is an okay tool. It has its strengths and weaknesses. It's the best supported tool on ARCHER2 because it's a Cray tool. It's not the only one around. There are other profiling tools. There's MAP. There's an installation of Scholastica, and some people also use one that you can quite easily install yourself that some people like is called HPC Toolkit. Is also quite an interesting tool to use. So there are other options other than CRAPAT. And we do sometimes run some tool-specific courses to give you a deeper. So this is just a very quick introduction to CRAPAT, but we do run courses which go deeper into some of these other tools. So yeah, you can look at routine level or loop level information. You can get some insight with performance counters. So what CRAPAT does reasonably well is it covers different programming models. So it works fine with it. It handles MPI plus OpenMP code quite well. But if you're using something weird, then it also works. And if you have so again, we do have some GPUs on ARCHER2. So if you're interested in using those, then CRAPAT also copes with some GPU programming interfaces. It gives you information on memory usage. Okay, yeah, and so yeah, remember the golden rules. Okay, so yeah, don't be a question. Not believing other people is a bit strong. Be healthily skeptical about received wisdom about where applications spend their time. It can often be wildly wrong. Okay, so does anybody have any questions? So Henrik's asking, or somebody at Imperial anyway, is asking, how important is pinning cores for profiling with MPI? Yes, so it is, but Slurm is doing that by default for you anyway. Okay. But on other systems, then you might, you probably, I mean, you do probably want to be pinning your MPI ranks anyway. So again, if you're doing something, if your production usage does something non-standard with pinning, then you should probably, you want to reflect that in your profiling runs as well. But the standard on ARCHER2, the standard Slurm scripts are set up in a way that it does sensible pinning of MPI ranks. It also does. It's also sensible for what I would call standard hybrid MPI plus OpenMP. So that if you use this again, if you use the recommended scripts from the ARCHER2 user guide, then the rank and thread pinning is all taken care of correctly for you. If you start doing weird, if you stray outside the sort of standard use cases, then you can run into some trouble. So if you are, if you think about, if you're underpopulating with MPI and you want to do something different from just spreading your ranks equally across NUMA regions, if you want to use particularly nested parallel regions in OpenMP can be a problem. It can confuse the binding of threads, can get messed up. So there are kind of there are corner use cases where the binding doesn't work as you might help, but say the standard use cases, the recommended scripts, the Slurm scripts do everything correctly for you. Okay, anything else? Okay, so Daniel says, yeah. Okay, what percentage is generally considered to be reasonable for L3 cache miss percentages? Yeah, yes. How long is a piece of string? You probably want to be looking at, if it's 10%, then you probably could think about that could be improved. Once it gets down below about 5%, then you probably think that's fine and not worth worrying about too much. Something like that. But it's, it's a little bit finger in the air. Oh, I would just compile with your production level flags. Yeah. Usually helps to turn. You get better information if you use -G, but you should still use full optimization. Okay, so if there aren't any more questions, then let's break for lunch, and Adrian will be taking over from me for this afternoon session at 2 o'clock.